Make sure that you familiarized yourself with the anatomy of the neuromuscular junction, because here we're going to look at the physiology. Let's label a few things on this diagram. This up here is a motor neuron. You can spell motor any way you want. And this is also the part of the motor neuron that's like the dead end, and we call that an axon terminal. Down here, this is the sarcolemma of the motor end plate. That is the area on which a neuron comes into almost touches it but doesn't. And these wavy lines here are also called junctional folds. And all they do is increase the surface area at the motor end plate. This is the synapse. We know that there are, you can spell that any way you want to, we know that there are vesicles in the axon terminal and that these vesicles contain ACH. Wait, we know that there is a voltage-gated calcium channel. We also know that down here there are ligand-gated ACH receptors. So here's the little place that ACH is going to connect. And we also know that these proteins down here are also channels. Okay, so let me switch to another color. Let's use purple, and let's put this in motion. So number one, an action potential, which is the movement of ions, it arrives at the motor end plate. That's number one right here. And this is number one. I'm sorry. It arrives at the motor neuron. Then the second thing that happens is this action potential opens up this voltage-gated channel, and it allows calcium to enter in to the axon terminal. So that's number two right here. The calcium causes the exocytosis of all of the ACH into the synapse, right? So the exocytosis is right here at number 3. And here is our neurotransmitter that is floating now in the synapse. At this point, I have done nothing to the muscle. All of these events, these 4 things, are the events that are happening in the axon terminal of the neuron. And all of these events result in acetylcholine entering the synapse. So here we are, continuing from the previous slide, and we have the neurotransmitter, which in this case is acetylcholine, and the neurotransmitter is diffusing from their area of high concentration across the synapse. As ACH crosses the synapse, it says, oh geez, there's a seat just for me. And what it does is it docks itself into these ligand-gated channels, right? It is the ligand. It is the key. And being a key, when acetylcholine connects to these channels, they open and they allow sodium to move into the cell. So number 3, which I have right here, kind of combines these two together, that the channel opens and now sodium enters into the cell. I want to make this very clear that ACH does not enter the cell. Put hearts and stars and balloons around this, because people forget ACH does not enter the cell. It's like a token, and you put the token in the turnstile, but you enter the subway. So ACH docks itself on the ligand-gated receptors, but it is sodium that moves into the muscle fiber. Okay, so here we have a continuation from the previous slide. We have sodium going into a cell, and when the cell becomes more positively charged, then we say that the cell is depolarizing. And that is actually, that's very true. That's what's happening here at the motor end plate, that ACH is connecting with ligand-gated channels, and it is allowing sodium to move into the cell, which is a phenomenon called depolarization. And this word means to become more positive. So if I can open up enough of these sodium channels, if I can get enough depolarization, like a lot of it, opening up one of these will not be enough. But if I can get enough of these ligand-gated channels to open up, then what ends up happening is they create this little charge that then reaches the voltage-gated channels that are everywhere along the sarcolemma, right? So I can create enough of a change in voltage to start these popping open and allowing sodium to enter into the cell. And I want you to look at this picture up here that's at the top right. Each of these areas are neuromuscular junctions. I'm going to stimulate them all at the same time. Acetylcholine is going to get puked out into the synapse at all of those neuromuscular junctions at the same time. And the depolarization is going to spread out from each of these neuromuscular junctions, making sure that all of this muscle fiber, all of this motor group here is going to be stimulated at the same time. So when we excite a muscle, we're not exciting one motor end plate. We're exciting many. And the purpose of exciting, and that's what this process here is, it's called excitement. The purpose of exciting at the motor end plate is to get depolarization to happen with those voltage-gated channels. Once that happens, then an action potential actually spreads through the membrane, and it can keep going along the sarcolemma. It can spread out. And what we've done here is we have taken an action potential that was in the neuron, we've turned it into acetylcholine that diffuses across the synapse, and then we've turned that back into an action potential in the sarcolemma. So basically, we have taken an action potential coming from the brain and put it into this cell. I wanted to mention that even though we've covered a bunch of steps here, we have not talked about contraction. All that we've talked about is the process of putting an action potential into a muscle, which does not guarantee contraction. It increases the probability of a contraction, but it doesn't guarantee it. So let's talk about diseases and muscle relaxers that work here at the neuromuscular junction. The picture on the left is great. I didn't make it. It kind of sums up with the picture, much like the one that we drew. This disease here that you see over on the right that I always mispronounce, myasthenia gravis. It's a neuromuscular disorder, and it results in muscle weakness, like I can't breathe muscle weakness, not like my leg hurts muscle weakness, right? So not just skeletal muscle, but other muscle. What happens, as happens with so many autoimmune diseases, is that some rogue B cell somewhere in the bone marrow decides to make an antibody that is not shaped quite right. And it ends up that the antibody has a region on it that can attach to the ACH receptors. And so the antibody, it does attach to the ACH receptors, and it basically just sits here blocking the ability of ACH to attach. Muscle relaxers that work at the neuromuscular junction, they do the same thing. They block the transmission of the action potential. And you can do that in so many ways. You can create a drug that sits here on the receptors blocking it, kind of like that autoantibody that you see there. You could develop a molecule that sits here preventing the exocytosis of acetylcholine. You could even block the calcium channels that are up here that are not on this picture. So there are so many molecules that you could make that block any of these processes that are supposed to happen at the neuromuscular junction. And that is what muscle relaxers do. They stop the stimulation. But what about stimulating the muscles of people that are inflicted with these diseases? All right, so we get the idea that the disease depresses stimulation. What can we do to increase that stimulation? That's a good question, to which the answer lies in one of you going into research at a pharmaceutical company and finding the answer. There is an enzyme that removes ACH from the synapse. It's called ACHE, or acetylcholine esterase. Right, so it's ACE ending, you know it's an enzyme, and it's basically just a molecule that breaks down or catabolizes the acetylcholine. We can stop this enzyme from degrading ACH. When we do that, our hope is that ACH will spend more time in the synapse, and it will increase the probability that ACH will come into contact with one of these ligand-gated channels. The problem is that for so many of these diseases that produce muscle weakness, that all of the ligand-gated channels are occupied. So even if we could make acetylcholine spend more time in the synapse, it wouldn't do anything. Because like this picture over here on the right, all of the ACH receptors, they're all occupied anyway. So you could flood this synapse with ACH. It doesn't matter. It would never, right? Increasing the ACH in the synapse would never contribute to more muscle contraction.